Hi guys, I wanted to record a short video covering the kinematic equations for constant acceleration. I'm not sure I'll have time to go over this material in class, and I think this video might be helpful as you work on your homework assignments. So the goal of the video is to derive the equations that describe the position, the velocity, and the acceleration when the acceleration is constant. Okay, so these are the kinematic equations. Under constant acceleration. Okay, so that's the goal of the video. So let's write down the equations first, and then I'll talk about some general properties that describe the kinematics and how the various quantities are related, and how to sketch them, and how to derive the equations that we need. So the equations themselves, well, the first one is easy. It's the acceleration. The acceleration is a constant, so A is a constant. That's easy. And it turns out that if A is a constant, then V is linear. V is equal to whatever the initial velocity is plus A times t. And if V is linear, then the position is quadratic. So x is equal to x naught plus V0t plus 1/2 AT squared. So these are the equations. This is what we want to derive. You should pretty much just memorize these. These are very useful. And we're going to spend the rest of the video figuring out where they come from. So the first thing I want to say is that these are all related by integrals and derivatives, okay? So I'm going to do the formal calculus first and try to explain where these things, what the geometrical interpretation is, okay? So let's first imagine that we have the acceleration, and let's say that I plot this acceleration as a function of time. Okay, so I know that it's a constant. That's the situation that I'm talking about. So let's just sketch a constant here, and its value, I'll just call its value A. And this is t on this axis. And let's just say that, you know, we'll pick some particular time that I'll call t. So, so it turns out that the change in the velocity, the delta v, okay, this is one of the big takeaways. So the delta v is equal to the area under this acceleration versus time curve for up to some time t. So let me write that in a formula. So delta v is equal to the area under a of t graph. Okay, and the calculus way of saying that is that this delta v is equal to the integral from some initial time to some final time of a of t dt, okay? And so graphically here, for our particular case where the acceleration is a constant, our initial time is 0, and our final time is t, and the area that we're interested in is this area. And that area is my delta v. Delta v is equal to a t, right? Well, delta v, by definition, is v minus v0, the final velocity minus my initial velocity. And so that is equal, that implies rather, that v of t is equal to v0 plus at. Okay, so this is our second kinematic equation. Our first one was obvious, right? A is just a constant. In fact, I could write that on this graph here. Right? A is just a constant. Okay, so this is our second kinematic equation. Let's now sketch what that graph looks like. Okay, so if I graph now the velocity versus time here, okay, the velocity versus time, then I'll get something that has some initial velocity, v0, and then it's going to grow linearly in time. Here on the previous graph, I said that the a was a positive constant on my graph. So that means that the slope here is also going to be positive. If I had drawn a down here somewhere, then that would imply a negative acceleration, and this slope would be negative. But here I've got a positive slope, so let's make this a positive slope here, okay? And that's my velocity versus time graph. It's a line. Its y-intercept is v0, and its slope is a, and it grows linearly in t. And so just as the change in velocity was equal to the area under the a of t graph, now the change in the position, in other words, the displacement, delta x, is equal to the area under the v of t graph. Okay? Now that area is formally defined as, again, the integral from t1, t initial, to t final of v of t dt. Okay. So I have to calculate the area under this line, and the easiest way to do that is to break it up into two pieces. So let me break this up into two pieces. Let's say this is a final time t, and now I've got this area here that I want, and I've also got this area here that I want. And this final t, at this final t, my velocity is, let's say v, my final velocity. So I need to calculate these two areas. This area here is easy. It's the area of a rectangle. So that is equal to v0 times t. This area here is the area of a triangle. It's 1/2 base times height. Right? So 1/2. My base is just t, and my height is the change in the velocity, but I can figure out what that is since I know the slope. Remember, the slope is a, right? The slope of this line is equal to the acceleration a, okay? And so I can figure out what this delta v is. It's just going to be a times t. That's the amount by which my velocity increases over a duration t. And so that's just 1/2 a t squared. So now the total area here is my delta x. So that's v0t plus 1/2 at squared. So this is telling me now that my x as a function of t is equal to my x0, right? Because delta x is just x minus x0. And so I'm going to move this to the other side, is equal, plus v0t plus 1/2 at squared. And that is our final kinematic equation. Okay, so there you have it, a geometric description of where these kinematic equations come from. Thanks for watching.